Yeah, our first speaker is Karl Landsteiner from Institute of Theoretical Physics, Madrid, and his talk is Gravitational Anomalies in Matter. Thank you.
Okay, thank you. Thank you for the invitation to all the organizers for organizing this very, very interesting and exciting workshop. Okay, so I was asked to do something provocative, and so I chose to put this title, Gravitational Anomalies in Matter, which my experience is that this is very provocative. Honestly, I don't understand precisely why, and I try to, make clear, hopefully that this is not as strange or out there as it sounds at first. Okay, the talk is based mostly on a review which will come out hopefully soon with my collaborators Maxime, Adolfo, Jago, and Maria. Okay. Yeah. Good. So why do we talk about gravity in quantum math? I will answer this. Yeah, one thing I also have to say, this was actually not planned, but my talk will basically go in parallel with Johannes' talk of yesterday. So it will sort of give the theory to Johannes' talk. And that was actually planned, but I realized in his talk yesterday that my talk fits perfectly to his, and so it flashes out the theory part to this. Then I will talk about anomalies in quantum field theory, and then what I call anomalous transport theory, and then I will apply this anomalous transport theory to these wild semimetals and derive a couple of consequences. But this will be more shallow than what Johannes did. Johannes did all the hard work, the experiments. Okay, and then I give a summary and outlook. Okay, so why do we talk about gravity in condensed matter at all? I have to say, I was very surprised. I come from very high energy physics, very formal mathematical physics, and when I learned that people in condensed matter routinely talk about metrics and things like this, I thought, what's going on? Why? You wouldn't expect that. And until somebody pointed me to this paper, and Johannes also mentioned this yesterday, by Luttinger from 1964, where he has this wonderful footnote saying, in fact, if the gravitational field didn't exist, one could invent it for the purposes of this paper. And this paper is the theory of thermal transport coefficients. And in this paper, the central equations which he writes down are these. So this is a bit unusual notation probably, but this Q means gradient. So he takes the gradient here. This is the electric potential. Mu is the chemical potential, T is the temperature, and again, T is the temperature, and then this is the gravitational potential psi. And he says that, so the effect basically of a gradient in the electric potential is exactly the same as the effect of a gradient in the chemical potential, or in this quantity mu over T. And the effect of a gradient in the gravitational potential, so the gravitational force, is exactly the same on a system near equilibrium in linear response, is exactly the same as a gradient in 1 over the temperature, right? So this is quite surprising. And where does this come from? It is surprising because it's only one derivative on the gravitational potential, and if you study gravity, Einstein gravity or something, you have the metric, and everything you can write down, which is a covariant expression, which you're allowed to write down, actually has two derivatives, like the Riemann tensor, and lots of indices and so on. And so why there's one derivative, and it's not totally clear in the Luttinger paper, but if you write down this, what is called constitutive relation systematically in the effective field theory sense, where you just say, oh, I write down all the terms that are really allowed by symmetries, right? And here I have a current. So the first term has no derivatives at all. It's just a charge, and u mu, you can think of it as a velocity. But basically what it is it defines the rest frame of your matter. So every matter, when you have a matter at finite temperature or chemical potential, implicitly there's also a rest frame defined with it. So that defines the rest frame of that matter. And this is some projection orthogonal to this rest frame, and then you have here basically Ohm's law, the divergence of the chemical potential. Then you have basically the thermal conductivity. But there's one more term you can write down now, because you have this rest frame vector, and this is this term, and that has to have a covariant derivative if you want to write it covariantly. And if you expand this term in a weak gravitational field around the flat metric, then you find these contributions, and they nicely sum up into something which is the time derivative of this guy, which is the space-time component of the metric, and the derivative, the gradient of the TT, the time-time component. So Luttinger has this term only in his equations, but if you do this fully covariantly, you get also this term. And the whole thing combines into what you would call a gravitoelectric field. So the upshot from here is that gravity can enter even because you have matter there, gravity and the metric can enter in this response at places where you wouldn't expect it if you think just in the vacuum, because in the vacuum you would have to form covariant tensors such as the Riemann tensor, and that would have many more derivatives. But gravity can enter at lower derivatives because of this. So it can be seen, can be there even if you don't see it. Okay, so here let me go quickly because this has appeared already several times, right? This is the usual chiral anomaly. I imagine I have chiral fermion, I put it in a magnetic field, the spectrum organizes here in this lambda levels. There's a Dirac sea. And then if I apply also a parallel electric field, I have the spectral flow in the lowest lambda level. I pump energy into the system, and the only guys which can move are these in the lowest lambda level, and they cross what I call normal ordered vacuum, and I view this as creation of particles, right? This is the standard picture. However, a small warning sign here. This picture ignores that there's a cutoff in the quantum field theory, which you always have to take into account, that will become important at times. Okay, so this is a theory talk, so there will be complicated formulas. I'm sorry for that, but I aim for a little bit generality here. So here, this is the full-fledged story of chiral anomalies. J mu is a current, and A is some flavor index. So think of it as being like electric current or axial current or whatever. You have a theory with a bunch of chiral fermions. There are flavor symmetries which are generated by this charge QA, and every charge comes with a current like that. So for example, axial current and QA is just gamma 5. And then you take the derivative, and on the quantum level, you find these expressions. So it's naively, you would think it's 0, but on the quantum level, it's not. And the same holds true for the energy momentum tensor. Again, I mean, there's this term which already is this covariant generalization of Joule heating, but there's this anomaly. And they're both parts of this. So here I also assume that each of this current is coupled to a gauge field, which also carries an index A. And I view these gauge fields here primarily as sources in the sense of quantum field theory, which couple to that operator. So the way one should understand this formula is that this is a Ward identity from which I can derive correlation functions in the quantum field theory. And the way I do it is I take functional derivatives with respect to the other fields, for example, these other gauge fields or the metric, and I generate correlation functions of the operator divergence of the current, which is by an operator, with other currents. Right? The anomaly tells me how these correlation functions look like. Surprisingly, that's the anomaly. The operator d mu j mu is not 0 as an operator. And that's a very important point. The anomaly is a statement on the operator level of a quantum field theory containing chiral fermions. So in particular, that means the anomaly is not gone if you switch off all these fields. It is still there. It is there on the level of some correlation functions. Here in 4 dimensions, in this usual case, it's there on the level of 3-point correlation functions between different currents. So one of these currents could be an energy momentum tensor. And in this sense, what is called the gravitational anomaly is there even in flat space. Right? It doesn't appear on the level of the expectation value of the expectation value of the divergence of the energy momentum tensor, it appears somewhere else in the 3-point correlation function of currents. So the anomaly is a little bit more hidden, if you want, but it's still there. It's an integral property of the quantum theory, and it doesn't depend on having external fields switched on or not. It's there. This anomaly is always there. It's called gravitational anomaly because it becomes manifest on the level of the 1-point function in a background where you have this. Okay. Okay. And it's very easy to calculate them because they are subject to non-renormalization theorem. So you just have to calculate such a triangle diagram. And this calculation you can do in flat space, in the absence of gauge fields, just with the usual Feynman rules. And the upshot is that there are these very simple anomaly coefficients, dA, BC, BA, which are determined by the charges with which the fermions couple to this different, with the charges under these charge operators QA. So it's the sum over the triple product of the right-handed charges minus the sum of the triple product over the left-handed charges. So this determines this type of anomaly, and this type of anomaly is determined by this. So you just have to sum over the charges of right-handed fermions minus left-handed fermions. Okay. Now this is still relevant. There was only last year a publication from this Primex collaboration, which tested the Karl anomaly in particle physics by the pion decay. This has also been mentioned, and this is the result. This has been published in Science last year. And you see here the prediction from the Karl anomaly, and this is the latest experimental result, which is in very good agreement, of course. Now, already in 1969, so this pion decay, you know, Adler, Bell, and Shakif did this in 1969, but in the same year already, Kimura in Japan, he did the following. He said, well, if the pion can decay in gravitons, in photons, it probably can also decay in gravitons. And he calculated what we call now the gravitational anomaly. But of course, this is completely suppressed by some ridiculous number of order of magnitude. So this will never contribute practically. Okay. Yeah, let me skip this for a moment. Let me see how I'm going in time. Not that bad. So let me go to this. So there is this issue about, which already surfaced during this conference a couple of times, what is goes under the name of covariant and consistent anomalies. The type of anomalies I've written before on the blackboard, they are called the covariant anomalies. And one of the problems with this covariant form of the anomalies, if you take the vector current of a Dirac fermion, which you would like to be the electric current, which you eventually couple to a gauge field, to Maxwell's equations, that current is not anomaly free. That actually has an anomaly because the corresponding anomaly coefficient, dABV, this is usually thought of giving you the axial anomaly, but you can permute, this is totally symmetric, you can permute these indices, and you could put the V index here in front, and then it appears here, right? And then it's the vector current. And that would mean that the vector current is not conserved. It's not a conserved operator. And that, of course, makes troubles because if you want to couple such an operator to a gauge field, you want that this operator is absolutely conserved. Otherwise, you run into mathematical inconsistencies, right? This is antisymmetric, this is symmetric, so this is manifestly zero. So the divergence of the electric current has to be zero. Now, happily, in quantum field theory, by a suitable choice of regularization scheme, renormalization scheme, you can generate a counter term, which is this type of counter term, so-called Baldin-Zumino polynomial. And that counter term, you have to add to this covariant current, and then this one is absolutely conserved as an operator. Right? So what vanishes in QED is the consistent anomaly, not the covariant anomaly of the vector current. Okay, let me skip the rest. Okay, now anomalous transport theory. So I said already that you have these anomalies are completely determined by these anomaly coefficients. Okay, now you can do this in various ways, very simple-minded, just calculate how much current you generate at finite temperature and finite chemical potential. So what I've done here, I have switched on for every of the symmetries which I have, I introduce a chemical potential. For example, it could be an axial chemical potential, an imbalance in the number of left and right-handed fermions. A corresponding magnetic field, again, this is a magnetic field, could be a real electromagnetic magnetic field applied externally to your material, or some effective field, like an axial magnetic field, which has the appear in these Weil semimetals. Omega is rotation, that's the angular velocity, and T is just the temperature. And then you can calculate how much current do you get in the symmetry number A, for example, vector current or axial current. And it turns out that there's a unique answer to this, and it's completely determined by, again, these anomaly coefficients. And also it works for the energy current. So that means that the anomalies have, if you are able to drive a system with anomalies into a state where you have some chiral imbalance, or suitably heat it up, then, or set it under rotation, then you generate these currents. And actually these currents are proportional to the anomaly coefficients. So they really, really probe the presence of anomalies. And so this leads to the idea that in order to probe for the presence of anomalies, it's not necessarily, it's not a necessity to switch on these background fields, right? I mean, for the gravitational anomaly, it's very difficult to control curvature, right? We can't do that. I mean, it's given here on Earth, we have some, but we can't really control it, not like switching on electric and magnetic fields. So that's impossible to control this, you know, the gravitational anomaly part through gravity by itself. However, here, it tells you that you can generate currents, and they are sensitive to the presence of the gravitational anomaly because they are generated if and only if the theory does have a gravitational anomaly. So in this sense, yeah, there is, okay. Yeah, and what's also interesting about these expressions is that they are dissipationless, so they don't generate any heat or entropy or anything like this. You can also show that when you put an obstacle into this into the flow of this current, the current actually doesn't care about it. If there's something, you know, where a usual electron would scatter elastically, these guys which make up these currents, they cannot scatter elastically, so they don't lose momentum or anything like this. The currents are completely insensitive to these obstacles. So this is the idea, and this is part of the title, or this actually explains the title. So what you can do is, instead of gravitational fields or electric fields in some strange symmetries, which are probably difficult to generate, you can substitute the external fields by matter, in the sense that you have real matter there, like in a chemical potential, so stuff, or you heat the system up. And it's still sensitive to the anomaly. Okay, and these expressions, yeah, they go back, I think, Vilenkin has first obtained that, and of course Dimas on that. So there are lots of people. There's a partial list. I'm sorry if I've got people who contributed to that. Okay, now I told you that you can easily do this calculation in quantum field theory and find this result, that there's this sensitivity to the anomaly coefficients. But of course, it would be nice if you have an argument which directly converts the anomaly into these currents, right? You start just with your input is just anomaly, and the information that you at finite temperature and at finite chemical potential, and derive from this information alone the form of these currents. And this you can do. And the way you can do it is, a crucial point about the anomaly is that as an effective action, these are all massless fermions we are talking about. And the effective action, so if the effective quantum, the quantum effective action of massless fields is a non-local object. So there's, at least if you insist to write it down in 4 dimensions, there's no non-local form. So it's some complicated non-local expression. However, for the anomaly, you can actually integrate it into a local form if you go to one dimension higher. And this is something which is very well known in condensed matter physics, right? Because you have this anomaly inflow or this bulk boundary correspondence, edge boundary correspondence, where you have a Chern-Simons term in the bulk, say, of a quantum Hall state, integer quantum Hall state, and on the boundary you have a chiral fermion with an anomaly, and the anomaly is precisely the anomaly of the Chern-Simons term in the bulk. So you can view this Chern-Simons term as the effective action of the anomaly, but in one higher dimension, because there is no local effective action if you stay in the same dimension. Right? So this is the Chern-Simons term, which has both type of anomalies, the usual one and this gravitational one. And now I told you, and you need a 5-dimensional space in order to make this local. And the question is, what is this 5-dimensional space? Well, and so up to now, I've used the information that I have these anomalies. Now I need the information that I am at finite temperature and at finite chemical potential. And that has to be the only place where this can be encoded here is this manifold, this 5-dimensional manifold. Okay. And the way it is done, this has to be a manifold. It has to have only one boundary, because on the boundary, I want to identify the boundary with the actual quantum system I'm talking about. So it has only one boundary. It should be, in a sense, a closed space, at least in the Euclidean section, so to be technical. There are certain consistency conditions on this manifold, which it has to fulfill when it wants to represent something being at finite temperature. For example, if you go to Euclidean, the time direction has to be a circle and the length has to be 1 over the temperature and so on. And there's basically a unique answer to this, which is a black hole metric in 5 dimensions, which I've written down here. And this is unique. So here I've written it down already, slightly perturbed by this gravitomagnetic field, which is represents a slowly rotating black hole. It's determined up to these functions G and F. And it turns out these functions G and F are completely arbitrary. The only thing that you really need is that you need to know is that there is a relation between the temperature and the horizon of this black hole, the so-called surface gravity. And this goes back to Hawking. This is this famous Hawking formula, which tells you that the derivative of this blackening factor on the horizon can be interpreted as the temperature. Okay, and then this is basically just what Luttinger did, saying that the gravitomagnetic field, if you take the, and then you plug this in and you calculate how much current you get from such an effective action, and this is the result. Okay, so first you have a magnetic field which comes in here, and here you get the difference of the temporal component of the gauge field on the boundary, and I'm sorry, and the horizon, and that is the chemical potential. And here you get the temperature, and it's a rotating black hole, and this is the angular velocity of this rotation. Okay, so if you translate this back to where we came from, where we had the temperature and the chemical potential, that's just these anomalous currents, and they are completely determined by these anomalies. Okay, so because this works, that's an essential insight from string theory that we did first in this ADS-CFT correspondence, but you can argue that this should be general. So the ADS-CFT correspondence works very well for strongly coupled systems, but anomalies are independent of the coupling constant. So this has to work at arbitrary coupling constant. So what concerns the purely anomalous response of the theory, that should be captured by this method anyway. Okay, and just to tell you how powerful this method is, so we derived this, and then, for example, for the correct formula for the Chiral-Wortley effect in this approach is basically one line. You get it for free because you have to do all the other calculations, and you basically calculate everything at once. And we got this immediately, and we got all the factors correct. Whereas in the original, when Vilenkin derived it, there was a factor 1/2 missing in the Chiral-Wortley effect for the energy current. And I took a full paper to do the quantum field theory calculation by Magnus and Valje to get this factor right. And in chiral kinetic theory, this was also a paper by Chen, Son, and Stefanov. And in this gravity setup, it's really basically one line. And so this also a little bit, I want to answer one of these questions Johannes said yesterday, is there a sort of unified framework where all of this falls together, you know, this gravity, temperature, transport, and all this? And in my point of view, it's this you know, this is exactly realized. This unified framework is the ADS-CFT correspondence, but the ADS-CFT correspondence for, say, if you want how much conductivity is there, right? It only can be applied to very specific theories which we know, which are strongly coupled and realized in string theory and so. But for these things, which are much more stable, which depend on very, very crude features of the quantum system, like that it has an anomaly and not much more, not of coupling constant. So here it works exactly. Okay. And there's much more to that, much more to the theory where I don't have time to go in. There's also a relation to much more subtle anomalies, global gravitational anomalies, which can be applied in some situations where this reasoning does not really work, like for Gravitational, for example. There is a relation to the way Wilczek, his view on Hawking radiation, he can derive Hawking radiation from gravitational anomalies, and so very similar way. And so then I don't have time to go into this. Okay. So now let's talk about Weil semimetals. I can be brief here introducing this, because Johannes did already a fantastic job yesterday telling us about this. Yeah, you know, we have these Weil semimetals in this complicated band structure. Here there's the Fermi level, and around here there are crossings of these bands. And near these crossings, you can describe the effective electronics by Weil fermions. And the Nielsen-Ninomiya theorem famously tells you that you always have to have the same number of left and right-handed fermions. Okay, so far so good. Then, so this is the string theorist sketch of what Johannes did yesterday, the naive sketch of this. So you apply, you know, you apply some temperature gradient, heat up, you have a Weil semimetal, you heat up one end, or you inject electrons on one end, so you effectively raise the chemical potential on one end, and you apply magnetic field, and then you measure how much current flows, how much more current you get as function of this magnetic field. Okay. Okay, so here's the theory to this. I used just the transport equations, or the conservation equations for the electron, for the right and left-handed fermions in each species. So for each left-handed Weil cone, so for the left-handed and for the right-handed, I set up an equation where I say the density of electrons is conserved up to an inflow of current, and its energy is also conserved. But this is not really true, because there are these intervally scattering events, which at some time scale tau change chirality of these guys, because in these Weil semimetals, the electrons are really Weil to some approximation. At higher energies, they are not anymore Weil, because, you know, in a compact space like the brillinoson, everything which goes up must come down. And so this means that this electron can go through this band here and go from a left to a right-handed. And if it gets scattered very hard on some impurity, it might change its chirality. So there is some intervally scattering time. And what I'm assuming here is that there's a relaxation time where the electrons relax, but they don't change chirality. Then there's an intervally scattering time, the time scale on which they change chirality. This is much longer than this one. And then in a much, much longer time scale, probably the electrons talk to each other. So under these conditions, I can set up these conservation equations with this relaxation term. And then I use just for the gradients of the currents, I use these anomalous currents, right? And I plug that in, I solve for it, plug it back in again, and then I can calculate if I fix the temperature gradient and the gradient in the chemical potential, I can calculate the conductivity. And this is the expression for the conductivity matrix, and he is some susceptibility matrix which tells me how the energy and the density depends on temperature and chemical potential. So that's the theory to this. You can make some checks, like for example, if you express it like this matrix fulfills this positive semi-definite, fulfills the second law, this Onsager reciprocity, and so on. Okay. you can also calculate this density matrices directly from, say, chiral kinetic theory, and this has been done by Spivak, Andrea, Ferrer, Lundgren, and Fiete. Or you can do this effective, or you can do all of this in hydrodynamics, and this was also mentioned. This goes back to a paper by Sachdev, Lucas, and Davison. Okay, but here I don't assume hydrodynamics. I just assume energy and charge transport. Okay, okay. So then, if it's weak magnetic field, I should not say much about this because this was discussed already yesterday in Johannes' talk. But I find very amusing is if I take these conductivities, for example, the purely anomaly induced electric conductivity and thermal conductivity, and I form what is called the Lorentz ratio. And I go to the limit of, but the temperature is much smaller than the chemical potential. So I go to the limit of large chemical potential. And then I find that this ratio becomes this particular number, where I reinstated the Boltzmann constant and the electric charge of the electron. And this is a well-known law in condensed matter physics. This is a so-called Wiedemann-Franz law, which most of you know much better than me. But I want to point out that here I derived it from very arcane expression, such like the number 176, 1 divided by 768 pi squared, which is the anomaly coefficient for the chiral fermion, and the expression for the temperature of a 5-dimensional black hole, according to Hawking. This is what went into the derivation of this from this perspective. And it reproduces this Wiedemann-Franz law in the regime where you would expect it. And similarly, what is called the Mott formula, which tells you how much voltage you get when you apply temperature gradient and don't let the current flow. Then you build up a voltage. This is measured by the so-called Seebeck effect. And again, there is a formula which is valid in say, standard condensed matter physics. And again, it has this particular prefactor here, this pi squared divided by 3. Basically the same prefactor. And again, all these anomaly coefficients, the formula for the Hawking radiation, all of this goes into it, and they conspire precisely in that way to reproduce this. So you can say the anomalies know about this 19th century condensed matter physics, which I find very amusing in a way. Okay, you can go also to large magnetic field. This has also been mentioned, and again, you find you find that this thermoelectric conductivity switches off, and you can also do thermal and electric conductivity. And what you find also is that this Wiedemann-Franz law becomes exact. So it's not only at large chemical potential where it holds, but it holds exactly in this case. And so here, these were the cases where you have basically no magnetic field, very, very low magnetic field, and then very, very strong magnetic field where all the electrons are in the lowest Landau level. But you can also do the sum over intermediate stages, this more and more, summing more and more Landau levels. And this has been done for the electric case, I think, by Dima and Kaushik, and also for the temperature case by Das, Singh, and Agarwal. So these expressions are also known now how this works when you have intermediate field strength and chemical potential such that you get, say, quantum oscillations in the magnetic field. Okay, these are the experimental results. Again, I should not say much about it because this was discussed completely yesterday by Johannes. So just saying that this theory seems to work quite nicely and gives the proper results, which can also be seen in experiments. Let me very quickly, I'm almost out of time, mention this. Yeah, I told you that you need this, this counter term in order to get the proper electric current. This also has effects. The most prominent effect probably, well, the two most prominent effects is if you calculate really the electric current in equilibrium, when you switch on just a magnetic field at chemical potential mu5, which is always what I do is the chemical potential, I measure it from the point where, say, each chiral fermion is from the point where the density of states is 0, so there's this crossing point. So that's the quantum field theory convention of measuring. So mu directly measures how big my Fermi surface is, and here as well from mu right. So there is this second contribution, which comes basically from the Dirac sea, and that cancels precisely this. So you get exactly this Bloch theorem, this famous Bloch theorem. The anomalies know about that and they fulfill the Bloch theorem. But you also get this Hall conductivity. So if you apply an electric field and you have this separation in the brilliance zone between left and right-handed fermions, you get this Hall current that does not cancel. That is really there. Okay. What more shall I say? I probably should stop because I'm pretty much out of time, right? So, okay, I want just mention one thing. You can also, I told you the electric Hall conductivity. Yeah, okay, my clock tells me I have to stop. But you can also apply this theory to the thermal Hall conductivity. And here in the thermal Hall conductivity, the point is that this comes uniquely from the edge states. You can also understand the edge states and the edge currents from this anomalous transport theory. And this theory tells you that you do get an anomalous Hall effect, which is proportional to, again, the separation of these while nodes. But contrary to the electric Hall effect, this is a pure edge current. So there's no bulk thermal Hall effect, which is sometimes also discussed. And from this point of view of this transport theory, anomalous transport theory, it's a pure edge effect. Let me just say this. Okay, I think I just stop here. Okay, thank you.
Okay, thank you for a very interesting talk. I think it seems that we already have discussion in Slack. So I see one, I think it's comment in the chat. So the comment is from Emil Matolo. So the comment is, the effective action of the anomaly can also be written in a local form in D equals 4 by the introduction of an additional local field.
That's right. Yes, right. Yeah, that's true. So in this case, okay, there's more theory to it. When you say you cannot write this as a local form, then it means you have a certain given field space, which are basically just these gauge fields, right? And then the anomaly is a non-trivial element of the cohomology of the BRST operator. It goes number 1 on that, blah, blah, blah. But if you enlarge field space and modify also the algebra, the gauge algebra, such that it acts on this additional field in a proper way, then indeed you can do it. And this is what is called axions. I have not considered here that axions are present. Okay, sometimes axions, sometimes this is, but I think an axion is a different field. It's not, here I really just want the electrons as propagating degrees of freedom, and at low energies, I want to have effective fields, temperature, and chemical potential. The axion would be an additional degree of freedom, which would certainly have an influence and would change the picture, but I don't see how this enters in how there's an axion in Weyl metals.
Okay, thank you. We have a question from Evelina.
So I have a question concerning this slide where you had this anomalous transport, which is very enlightening, I think, for solid state physicists anyway. So, I mean, do I understand correctly that what you said, that ADS-CFT, if I have a topological action, and topological terms should also work when I have weak interactions?
Yeah, so my idea is that while this was done originally saying ADS-CFT, and this depends, of course, for everything which is non-topological and
universal,
determined 100% by the anomalies, that of course depends on the value of the coupling constant and on the precise degrees of freedom and all of the microscopics. However, the anomaly just depends on very, 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 say, on topological information of the quantum system, right? And it doesn't matter if you're at strong coupling or weak coupling, there are all these non-renormalization theorems. So the idea is that this, what you do actually originally in the ADS-CFT, it's applicable in general. Only, and I emphasize only for these anomalous terms, right? I cannot calculate an ohm conductivity for a real physical systems like that.
Sure.
Right? But the anomalous, and there are several instances where this method actually gave the right result, and the field theory had to catch up after some years and confirmed what this is.
Yeah, this is very beautiful. But, and I mean, from this, you also derive this Wiedemann-Franz relation and so on.
That's
How
right.
would Exactly. So how would you get now violation of the Wiedemann-Franz relation? Can you still get it?
Yeah. Well, you know, but it's I don't know. I'm not an expert on this, so sometimes metaphysicists correct me. I say complete stupidities here. But of course, Wiedemann-Franz is the way I derived it, at least here, and the way I understand it. It's a relation which is valid in a certain parameter regime, especially when you're at very large chemical, when the temperature is much smaller than the chemical potential. So if temperature would be large, then that wouldn't apply anymore, right?
Yes.
Or if you're really at the semi-metal, right? Like I think in Johannes material, this iron phosphide, it has very small, almost zero, right? Chemical potential. So if you're really semi-metal, where your Fermi level is exactly at zero density of states, then I would not expect Wiedemann-Franz to be valid.
Sure, I agree. But could I derive it still for using this Hawking radiation?
I mean, these expressions are more general than that. Wiedemann-Franz is just a limiting case of the general expression.
I see. I got you now. Now I got it, what you mean. So you would just get more complicated relation if you...
You see here, these are these complicated relations, which are valid when the magnetic field is small.
Very, very nice. Thank you.
Our next question by Baptiste.
Yes, thanks for the talk. I have two questions concerning your slide about chiral anomaly. First of all, in the expression of d mu t mu alpha, you only have a term which is proportional to r multiplied by f. Isn't there some term which are proportional to r squared? So to r squared.
No, I think I got this correct. You see, you can memorize this because these are mixed anomalies. And like the axial anomaly is a mixed anomaly, you always have one axial, a 5, and two vector, VV, right? And for the gravitational anomaly, in 4 dimensions at least, so this is in 4 dimensions, it's similar. You have here the current, and here you have two curvature tensors. And if you look to the corresponding current, which in this case is the energy momentum tensor, this quantum number has to appear here in the curvature. So you get one curvature, usual sort of curvature, and one gravitational curvature.
Okay, thanks. And second question, you talk about the gravitational anomaly, but the gravitational anomaly has many different phases, such as the trace anomaly or veil anomaly also. Is there a link between what you said and the trace or conformal anomaly we can also expect in these systems?
No, a priori, these are different kind of anomalies. So you will still say you can have systems which do not have this type of chiral anomalies, but they will still have conformal anomalies. So to my understanding, they are different. I also would not know, for example, how to make an argument like I did for this type of anomalies with this Chern-Simons. I'm not aware of, for the technicalities, I'm not aware of this formalism of descent equations, which underlies all of this, which work for chiral anomalies. I don't know, I don't see how this could work for conformal, but probably Emil knows more about that.
Yes, I can just comment. The conformal anomalies are very closely related to these. They are different, you're right. But for example, long ago, we analyzed the triangle diagram with the stress tensor, and the conformal anomaly enters in essentially the same way, keeping track of all the indices, essentially the same way as the Adler-Bell-Jakiv anomaly. What you don't have is a topological protection that I'm aware of, that you can say that it's non-renormalized. It will depend on the beta functions of the coefficients. But other than that, it's very similar, I think.
Okay, yeah.
I also, if I may, I wanted to just comment on what you said before. First, interesting talk, of course, thank you. But also, you know, this local field that we discussed in several papers, it actually is there already, even if you don't introduce a Weinberg-Wilczek axion. And you can see that in the fact that the triangle, the ordinary ABJ triangle, has a 1/k² massless pole. So the propagator of that massless field is already there, and you just make that more explicit by writing it in terms of a local scalar, a local pseudoscalar.
Okay, so you can integrate it in and make the actual local.
Right.
Yeah.
And that's actually very interesting because it shows that there's some kind of correlated two fermion state. If they're massless, they're moving essentially collinearly with the speed of light, and they act like a scalar. It's like a Cooper pairing.
I see. Okay.
We can
Sorry.
discuss.
Okay.
Okay. Thank you.
We have, I guess, last question from Christian.
Yes, hello. Thanks a lot for the nice talk. I just want to double check on basically what was just said on the topological protection. Somewhere you mentioned a 't Hooft anomaly. So is this a 't Hooft anomaly? So is it protected entirely? Are just the coefficients DABC protected under RG flow, or is
I have a slide about this. I didn't say it, but I have it here. So what is renormalized and what is not renormalized? So what I'm talking, so 't Hooft anomaly matching. I mean, from my point of view, there's only one kind of anomaly, and that's a property of the quantum theory of the fermions. Now, the question is, do you gauge that particular symmetry, right? Couple it to a dynamically gauge field, right? Then sometimes people give different names, like then they say ABG and things like that. But the anomaly is always the same in the fermion system. But of course, when you have dynamically gauge fields, then of course the coupling constant will get renormalized. However, what is not renormalized are these charges QF, A, which determine the anomaly coefficient, right? They are the same. And for example, in QCD, if you look up the quark charges, these are these numbers. You know, the up quark has 2/3, the down quark minus 1/3. These numbers, they stay, they are not, and they determine this anomaly coefficient. But of course, the fields, the external fields which couple to this triangle diagram, they will get renormalized by all the dynamics of the quantum theory.
Okay, thanks a lot. That answered my question.